Yes, so indeed, so there was a little change. Don't worry, Peter is doing just fine. He's right there, by the way. He didn't age by 15 years overnight. No, he's fine. But he really insisted on speaking tomorrow morning right after the bouillabaisse. So I had to accept. So, and I want to apologize in advance. So as you see by my title, there's going to be no embeddings, maybe some at the end, very little, and no knotted objects. So it's not a talk that is very much in the topic of the conference, but I do think that this is it's something that I'm working on right now. It's joint work in progress with Adrien Kassel. And I do think that it does fit in the conference because the aim of the talk is to show you that some tools that are quite basic in topology can be used for other purposes. I mean, not completely standard purposes, and that is to have result in combinatorics and furthermore maybe in statistical physics. So let's see to where I get. So maybe I'm just going to start with an introduction. Basically setting up the notations and reaching the theorem I want to prove, I want to show you. Okay, so in all the talk, gamma is going to be a finite graph. V is for the set of vertices, E edges, so it's a finite connected graph. And I will consider a family of edge weights. So edge weights. I'm not going to be extremely precise. This you can consider either you can think about this as non-negative real numbers, or you can just think of as formal variables. Okay, let me just recall what you all know, that is the definition of a spanning tree. So a spanning tree of gamma is a connected subgraph T of gamma with no cycles, and that is covering all the vertices. Okay, this you all know. And with this, you can build the associated partition function. So the, let's say, spanning tree partition function as well. So you take, I'm just going to denote it this way. Spanning tree depends on the weighted graph. And this will be the sum over all such trees of the weight of the corresponding tree, and that is the product of the weights of all the edges in the tree. Okay? And this you can see as living as a polynomial in the x's. So you can see as living in this polynomial ring, which I will simply denote like this, and this I will simply denote by x of t. Okay, and just a quick obvious remark. If you set all the weights to be equal to 1, then this partition function is what? Well, it's simply the number of spanning trees, right? Okay, very good. So there's another combinatorial object I want to recall the definition of. And this is something called a rooted spanning forest. So I guess you can guess what this is. Let me just recall a rooted spanning forest so on of gamma is so a subgraph f of your given graph with no cycles, covering all the vertices. So that would be, let's say, a spanning forest. And the word rooted stands for you want to mark a specific vertex in each connected component of f. Okay? So with a distinguished vertex in each component. Okay, and so obviously I'm going to give you an example right now, but just so, of course, then you can build the corresponding partition function and just do exactly the same. So you do, so it's a rooted spanning forest of gamma x. This will be the sum over all these forests of the weight of the forest, that is the product of the weights of the edges of the forest, and this lives in this polynomial ring. Okay? Very good. So let me give you an example or a couple of examples.
You don't pay any attention to the roots.
I'm sorry?
The roots of the trees are irrelevant for that polynomial.
Yes, so for trees, I don't look at rooted. Okay, here, yes, you're right, exactly. So here, if you prefer, you're summing over. Yes, so you're right. So the root. You count it again if you have, that's exactly what I mean by with the distinguished vertex, okay? So maybe it's going to be clear with an example. Okay, so let's just look at a very simple example to start with. So let's just look at this graph. Okay, let's compute these two partition functions. So for a spanning tree, what do we get? Okay, so you have two spanning trees, one like this, So you get x1 plus x2. Okay? And then if you compute, maybe I'm just going to do this here. Well, okay. So if you compute the rooted spanning forest partition function for this, what do you get? So you get one forest which has no edges. This would count for 1, and then you get so you have this one, but you also have this one. Okay, so here I count twice because two roots. So I think this answered the question. So this will give me 2x1, and then I'm going to have 2x2 for the two other ones like this. Okay? Okay, let me just give you another example. Let's look at a cycle of length 4, and I'm going to set weights like this, x1, x2, x2. Let's try. So spanning tree here, let's see. I will get one like this, one like that, one like this, one like that. So I'm going to have twice x1 square x2 plus twice x1 x2 square. Okay? This I can write as twice x1 x2 times x1 plus x2. And now let me see. So I'm not going to compute explicitly this partition function because it's a little bit long, but I'm going to give you the result. This is 1 plus 2x1 plus 2x2 times 1 plus 2x1 plus 2x2 plus 4 x1x2. And what do you see here on this example? You see that this one always seems to be a multiple of this one, right, in this polynomial ring. And you see what you have here, of course, I chose things. I chose this example because this one is a double cover of this one. And what I mean by this is that I took the weights also of the bottom one and I lifted them here. And it does seem that, well, we have this phenomenon that if you have a finite covering of a graph, binary graph, then the partition functions divide, well, the bigger one, well, the up one will be divisible by the one at the bottom. Okay. And so this is a theorem that I would like to basically to prove today. So let me state the theorem in a complete way. Okay, so theorem. So again, this is joint work with Adrien Kassel, who, by the way, is the son of Christian Kassel, who's doing knots. Maybe you know him. So the theorem is, so let this be a finite covering between two finite connected graphs. I'm going to say weighted graphs, okay? And I mean by this, I have put weights there and I lifted them for the other. So maybe let me just switch the notation. Let me like this. Sorry, I hope you understand. So it's a finite covering map, and then you lift the weights of the bottom one to the top. So two finite connected weighted graphs. Then spanning tree partition function of the bottom one divides the spanning tree partition function of the top one, and same thing for the rooted spanning forest divides rooted spanning forests of the top one, and each time I mean in the ring, in this polynomial ring. And of course, the very nice corollary is that if you set all the weights to be equal to 1, then you get that the number of spanning trees at the bottom divides the number of spanning trees at the top. Okay, so corollary. The number of spanning trees in gamma divides the number of spanning trees gamma tilde, and same thing for rooted spanning forests. So this is an immediate corollary, just set all the weights equal to 1. So of course, when you find this kind of result, you're very excited. You find it's really, really nice, and we were. And then you start looking in the literature, and of course, you find that at least the first one was already known. So the first result here was known, is due to Berman in 1986. But the proof is quite different. So he doesn't even talk about coverings. So it's really it's combinatorics, and he has conditions on the two graphs, and you can check that, well, if you have a covering map, these conditions are satisfied, so indeed his proof is working. And it's only for the number of spanning trees, it's not for the full partition function. Okay. And to the best of my knowledge, this one was not known, but okay, I might be wrong. Good, so that's it for the introduction. I don't know if you have questions about the statement, or it's fine, yes? I'm sorry? This is difficult to say. So, so you will see that in the proof, you will see that there is an explicit, we have, the quotient is equal to the determinant of certain matrix. But then it's hard to say, in general, I cannot say, I cannot express this quotient combinatorially. I don't know. It's possible that, yeah.
Does it always have positive coefficients like in the example?
I'm sorry?
Does it always have positive coefficients like in the example?
That's a good question. I don't know. I don't know, but it might be.
Can you recover the order of the covering somehow?
This I have to think. Probably it's the case, but I'm not. I'm sorry, I'm not sure. But you will see. I mean, there is a lot more information in the proof than in the statement. So I think the answer is yes, but I cannot say now. Yeah. Okay. So okay. So now I will come to a slightly technical part, which is basically just introducing the tools for the proof, and you will see again these are tools that, well, you might have seen already. So that's twisted, or let's say Laplace operator, discrete Laplacians. Let's say n coverings. So my aim now is to introduce something called the discrete Laplacian, which you might know, and to say that actually we have a result that tells you exactly how this discrete Laplacian behaves with respect to coverings, and then we can use this. Okay. So again, we have this weighted graph as before, as above. Let's say with let's say n vertices. And so the associated discrete Laplace operator, discrete Laplacian, I'm going to denote it this way. So it's a map on this space, is defined by, so let's see, so I have to take a function here, and then this defines an element here, so I have to feed him a vertex, and now he needs to give me a complex number, and this complex number is the sum over all oriented edges starting from V, so I'm going to denote like this the oriented edges, xe times f of V minus f of W. Okay, you might have seen this definition already. Okay, very good. I'm sorry?
Now your graphs are oriented?
No, so the graphs are never oriented, but here simply I want to, well, simply in this, here you see V and W don't play the same role, so I'm just writing this way, okay? It's just, if you prefer, it's really the same as looking at all the neighboring vertices, okay? I sum over all the vertices that are adjacent to V. Okay. Okay. And now there is a theorem which is due to Chun and Langlands, 96, which states the following. So it's so let me state it. So if I look at the determinant of this operator plus ti, so it's something like the characteristic polynomial, it's not exactly this. Let's write this as what, dn plus dn minus 1t plus etc. plus d1 tn minus 1 plus d0 tn. So that's just to fix the notations of the coefficients of this this polynomial. And now what this theorem gives, it's not exactly in this way that they stated it, but it implies what I'm going to say, is now combinatorial interpretations of all these coefficients, okay? So with di being a sum over rooted spanning forests. So I look at all the rooted spanning forests in gamma, but I restrict to the ones that have I edges. okay, with I edges. Okay, is the statement clear? So we're going to try a couple of examples, but
But what is the set of what is the set in row?
So if you prefer, so since this seems to be a little bit annoying, so I'm just going to say, so I'm just going to sum over all W that are adjacent to V. Okay, and here I make this difference, and here instead of E I will write, well, this is the edge VW. Okay. I think it's in an.
So then the sum is really on, because if you reverse, so how is the orientation of it? So with the first definition, so if you take all possible orientation of edges, then I would get 0. And so because here you have to choose between, so are you summing over the pairs, or the ordered pairs, the non-ordered pairs?
So V, so here V, right? Okay. So I think, okay, good, thank you.
I think if you take the sum over all V, then this is going to give 0 maybe.
Yeah, so that's right. So this was one. So that's exactly the meaning of this thing here being 0. We're going to look at this. Okay. So let's see. So let's just make a couple of examples here to see if it makes sense. Okay, just like reality checks. Okay. I first should say something. When we see this name, I don't know about you, myself, I get scared. Think, well, that's hardcore stuff. Okay. So maybe if this was a job talk, I wouldn't say anything. I would say, okay, Langlands, and then it's in the audience. So not at all. So this theorem is extremely easy. It's very, very easy. So he also did some easy stuff, and so this, okay. So this is basically just applying Cauchy-Binet to factorization of the Laplace operator as two operators. It's really not difficult. Exactly. So this is something else I wanted. Yeah, exactly. You're right. So okay. Let me try to make some examples. And indeed, that's simply a generalization of the matrix tree theorem, also known as the Kirchhoff theorem. So examples. Let's take the n equals 0 case. So d0, what is it? d0, this is the determinant of the Laplace operator, right? And this, as Raphael said, so actually, if you take the Laplace operator and you sum of all the lines or all the comments, you get 0. So its determinant is 0. So this is 0. And does this make sense? No, sorry, it was dn. I'm sorry. I meant dn. This is 0. And, well, here, indeed, if you want to have a spanning forest over n vertices, you cannot have n edges. It's going to have a cycle. So it makes sense with this thing, okay? And so here, indeed, no spanning forest with strictly more than n minus 1 edges. It's just an Euler characteristic argument. It's very easy. Okay, well, that's so far so good. Let's look at d0. So d0 from this equality, you see immediately it should be 1, right? Just by staring at this polynomial. So d0 is equal to 1. And here, well, let's see, we're summing over all rooted spanning forest with 0 edges. Well, okay, there is only 1, right? It's just a set of vertices, and its weight is 1, so it makes sense. Okay, that's okay as well. And now let's look. So that's of course just pure reality check. And now let's look at dn minus 1. So dn minus 1, what is it going to be? So it's the sum over all f with n minus 1 edges. Rooted, sorry. So f is rooted. Sorry, that's just not visible. Okay, but the spanning forest over n vertices with n minus 1 edge, that's the spanning tree. Okay? So this is the same as the sum over all rooted spanning trees x of t. Okay, but so now each spanning tree is connected. So it has, each connected component has n possible roots. So here what you get is actually n times the spanning tree partition function for your graph. And this is what is called the matrix tree theorem. Okay? So this, or Kirchhoff. So indeed, you should think of this theorem as a generalization of the matrix tree theorem, and the proof is the same. Okay, and maybe one more remark that we'll use. Now, if you look at the determinant, if you set t equal 1 in this equality, what do you get? You get d n plus d0. That's the sum over all rooted spanning forests. So that's exactly the partition function for rooted spanning forests. And of course, this is really the reason why we're looking at these combinatorial objects and not others. It's because you can count them with the determinant of an operator. That's it. And everything I'm going to say today, basically, whenever you have an operator whose determinant or minors can count an object, basically what I'm saying is extending, more or less, so with some. Okay. Good. So now what I want to do is consider a twisted version of this operator. So it's right here. So twisted. So what do we need? Okay, so let us fix rho, which is a homomorphism from, well, let's say a finite dimensional complex representation of the fundamental group of the graph. Okay, a finite dimensional complex representation of fundamental group of the graph. And okay, what I want is to twist this formula that was not so popular, difficult to understand. I want to twist this with this representation. And okay, here it's kind of difficult just to have the representation itself. So what you need is to represent this homomorphism via something called a connection. So you want to have a, so let me just write this down. It can be represented by a connection that is, so I'm defining now what this means. There exists a set of, okay, so here again I'm going to use this notation. So for each oriented edge, now I really want to be precise. For each oriented edge here, I associate an element in GLW such that if you reverse the orientation of the edge, just take the inverse. So that's what is called a connection. And then I want this connection to represent my homomorphism. That means whenever you see, the monodromy of this connection is equal to rho. Okay? So let me write it this way, whose monodromy okay? And now I can use this this board again. So maybe just use a color. Now the discrete twisted Laplacian, I'm gonna write a rho here to remember that it's twisted by this this representation. Okay, so now it's not going to be C here, but W. Okay, and I use exactly the same thing, but now just here f of w. Here I want to act with this automorphism of w. Okay, so let's see if this makes sense. So now we have v, which is a vertex. We have f, which is an element in here. So I feed it this vertex. I want to get an element that should be in w. Let's see. So this thing here, this thing lives in w. I act with this automorphism, so I am still in w. Then I just make this difference in w, and then I multiply by this scalar, so that's fine. I get an element and I sum. That's enough. Okay, so this thing makes sense. Okay. So there are several remarks to be made about this twisted version. The first remark is that, as you see, there is a slight abuse of notations in the sense that I have I denote it by a row, while really what I'm using is a connection representing row. So this is not so bad, because one can check, it's not very difficult, that if you take two connections whose monodromy gives you row, then the associated twisted Laplacian are conjugated by an automorphism of the big space WV. Okay, so maybe I'm going to write this down. So that several remarks. The first remark is what I just said. So if two connections represent the same homomorphism rho, then the associated operators are conjugate. Okay, and of course I guess you all, this is, okay. Okay, by an automorphism of this big space. So what we're going to do at the end, of course, is take determinants of these things, so we're safe with this. That's not a problem. Okay. That's the first remark. The second remark is completely obvious. If you take the direct sum of two representations, if you twist your operator with the direct sum of two representations, what you get is basically where it's conjugate to the direct sum of the corresponding twisted operators. Okay, that's quite direct. And the third remark is just by definition, if rho equal 1 is the trivial one-dimensional representation, then the corresponding twisted Laplacian is the untwisted one, right? That's just the definition. If you just put 1 for all the identity for all these phi's, then you get the untwisted one. Okay. Okay, very good. So now I can state the. No, I need a couple more things. Okay, so that's the twisted Laplace operators. So good. And now coverings. Yeah. I'm sorry?
It goes from WB to WB, but what's the XEs?
Don't what?
XEs, when you really work over.
Okay, so you're right. So if you want to make things very formal, if you want, you can work over the base ring of polynomials, and you can look at these things as modules over this ring. So this works completely fine. It's just, that's exactly the sentence I said at the beginning. I will not be very precise with whether they are real numbers or formal variables. You will see that the proof, for what I'm doing, it's completely fine. But indeed, for really formally, you could really look at modules over the ring of polynomials if you want. Yeah. So I do, but I think they don't. So they will never.
I'm worried about the long-running with the oriented edge.
Yes. So anyway, so you allow this, but then they will not appear in anything in spanning trees or okay. Good. Okay. So now I'm going to remind you something that you all learned in algebraic topology 1. It's the fact that if you have a covering map, it induces an injective homomorphism on fundamental groups. Okay, that might be long ago, but if you all remember this. Good, that's the only thing we're going to use here. And then one last thing, finally. If rho is a representation of a subgroup H of bigger group G, then there is something called the induced representation. Then it induces a representation usually denoted by rho sharp from G to GLZ. So I'm not going to define this thing because anyway it's not going to play such a role, but it just should know that, or maybe you know already, that whenever you have representation like this, then it induces representation on the bigger group on some bigger space here. Okay? So this, well, anyway. Okay, the dimension of this space here is equal to the dimension of this one times the index of H in G, and okay, you can. Okay, so now I can state the theorem. So I'm going to denote it by theorem 2, and I'm not going to put my name in here, just because, I mean, really, to the best of I've never seen this theorem written anywhere, but frankly, I would not be so surprised if somebody at the end of the talk, or not so nicely right in the middle of the talk, would tell me, of course, it's known here or there, really. So it's a theorem. It took me a while to figure it out and figure out the proof, but it's okay. The theorem is very easy, so I mean, to state, so given any finite covering map and any representation rho that you fix on the group of the top, that is the smaller group, then so if you want to understand the twisted Laplace operator on the bigger graph, twisted by this small representation, this is conjugate to the Laplace operator on the smaller graph, twisted by the bigger representation. Does this theorem make sense? This is true for any representation, finite dimensional, let's say. We're only going to use it for the trivial representation here. And we're only going to use it for the discrete Laplace operator, but it extends to a huge number of operators. There is nothing magical about the Laplace operator here. Basically, if you have discrete local operators, it will work. Okay. So again, here, I'll just say extends. Yes?
So the two Laplacians there, different spaces, right? So
That's right.
what do you mean by that?
So you have a commutating diagram. So you see, so you have W, so let's see, WZ, I think, okay, let's see. Okay, so this one will act on, so it's by rows, so it's W tilde W tilde WV tilde. UV tilde, so that's the one at the top, like this. And then the one at the bottom, you have a ZV, and have this. And what I claim is that you have natural isomorphism here that makes the diagram commute. Okay? Yeah, thank you. I mean, that was not so precise, yeah. So again, it extends to other operators. That's the things I was planning on explaining a little bit afterwards, is that, so really myself, I'm not a specialist of the spanning tree model. My thing is more a dimer model, perfect matchings like this. And it turns out that the dimer model does have also the good taste to its partition function is equal to the determinant of an operator. It's not the discrete Laplace operator, it's called a Kassel operator. And so these kind of things work also. It's not as nice and it takes longer to explain, so that's why I chose this one. But again, it does extend to several things. Okay, so I think I'm ready to give you basically the full proof of the theorem, if you agree. So third part. So proof of theorem 1. I'm not going to attempt to prove this one. It's not very difficult, of course. It's just basic fundamental group. Yeah, it's the usual dictionary between fundamental groups and covering spaces, and just apply it the right way. Okay. So proof of theorem 1. Remember, the theorem 1, it's divisibility for covering spaces. So let gamma tilde or gamma be a finite covering. Okay, both are connected. You have weights that you have lifted. I'm not going to write this again. Okay, so now we're going to apply this theorem to rho equal 1. So consider rho equal 1 on pi 1 of gamma tilde. Okay, so it induces some representation rho sharp of pi 1 of gamma. And so I didn't define this induced representation, but I'm just going to use now one thing, and it's very easy, but it does use the fact that this covering map is finite, it's finite degree. It's the fact that this representation has a one-dimensional invariant subspace. So it's because this thing is finite, it implies that rho sharp admits a one-dimensional invariant subspace. Okay, so that means that rho sharp is isomorphic to a trivial one-dimensional representation plus some other representation rho prime. Okay, and now we're almost done. So now, of course, I'm going to use these remarks. So now I will just use the theorem and the several remarks I made about this twisted Laplacian. So let's see. And then there is a nice little trick, and then that's going to be it for the proof. So, okay. So where do I start? So let's see. I'm trying to understand the untwisted Laplace operator on the big graph. So this is the same as the one twisted by the trivial representation. Now by the theorem, This is conjugate to this. I'm sorry, there's a tilde. Like this, okay? And now we just saw that this one factors as a product, so this is the same as 1 plus another one. Now there was a remark that was explaining that this is the same as this. Plus this. And this, of course, is the same. Okay? Okay, very good. So now this implies that if I look at the determinant of this thing, whom we know by the theorem of Chun Langlands that this counts some interesting objects, this will be the same as determinant of, so the corresponding thing for the smaller graph, for the times determinant of okay? And this thing is now, okay, so this, it lives in C of xt. Okay, and now comes the remark of Stefan. Okay, it is true. Now it depends how you formulate things, but that's a fact. Okay. You can also just say it works for any x, and then you have this equality. But okay. Okay, very good. So at that point, you think we're good. We're done. I mean, we just set t equal 1 here, and we have that this polynomial divides this polynomial in C of xt, and then you set x equal 1, and you get that the number of spanning trees here divides the number of divisible by the number of this spanning trees here in C. So, and that's not such a big achievement, right? Having divisibility in C is not that great. So there is a little bit more work to do at that point. And what is it? So I'm just going to write this as p tilde. This is p. This is f. And let's just think again what we have. So we have that p tilde is equal to p times f in C xt. Okay, and then what do we know? So we know that p and p tilde, actually, they belong to, if you just look at the definition of this thing, they actually belong to z tx. Okay, it's just by the definition. But then if you look at these two equations, what do you get? You get that f. So f itself, just by the definition, it's a polynomial in tx. But if you look now at this thing, it's the quotient of two polynomials in z. So it means that it also belongs to q of tx. So this is, so it's a rational polynomial in these things. Now you look at all these things. We have this equation here. We have that these two are here. We know that f is here. And we have one more thing, p. If we look at p as a polynomial in T, it has a leading coefficient which is 1. In particular, the greatest common divisor of all its coefficients is 1. Then we're in a situation where you can apply something called the Gauss lemma for polynomials. So p has leading coefficient 1. So you take all of this together, and now this implies, it's called the Gauss lemma, that actually f also has integer coefficients. And now basically we're done. So what do we have? We have that p tilde is equal to p times f in, so with everybody ztx. And so now we're good. So the part about rooted spanning forest is completely immediate. So now you just set t equal 1. And what do we get? So we get that, so the rooted spanning forest function for let's say gamma x. This is the determinant of gamma plus I. That was the remark. That's this consequence of Chun Langlands. This is P of 1. This divides P tilde of 1, which is the rooted spanning forest for the bigger one. And then if you want to have the result for the spanning tree things, you have to first multiply by T inverse and then set T equals 0, and then it gives you basically, so then multiply by T inverse, set T equals 0, and then you really apply the matrix tree theorem, and basically that's, so gives the spanning tree statement. Okay? Good. When did I start? Do I have?
You have another 9 minutes.
Okay, very good. So I hope you agree that it's kind of a nice trick, even though again it's not. I mean, again, it's just applications of quite well-known stuff in basic algebraic topology, but to things you would maybe not apply to. So now I would just like to tell you in the remaining minutes some other applications of, basically other applications of theorem 2. And here, okay, so let's see, that's part 4, other applications. So as I said before, what I really like in, or know better in statistical mechanics is this, is not this spanning tree model, but it's the dimer model. So I'm just going to recall for you what this model is about. So let's say a perfect matching on a graph gamma is a set of edges such that each vertex of the graph is adjacent to exactly one edge of M. Okay, just a little drawing, little example. That will be an example of a perfect matching on this graph, okay? And if your graph is weighted, then you can, of course, consider the corresponding partition function. So the partition function, we're going to write a D here because people working in this area call this a dimer model. So they call perfect matching, they call it dimer configurations. So this, if you have weights, this will be defined as the sum over all perfect matchings of the weight of the matching. Okay? So that's good. So why is this model actually studied? It's for a very simple reason, is that, as I already said, actually this partition function can be computed as a determinant of a matrix, of an operator, in the same way for a partition function for trees. There is one big difference, and here I'm a little bit in the topic of the conference, is that the graph must be planar. So if the graph is embedded in the plane, then this works. If the graph is not embedded in the plane, well, if it's embedded in a torus, you would need 4 determinants. If it's embedded in a surface of G, you would need 4 to the power G determinants and a kind of a linear assigned combination of them. So it's a little bit more tricky. But at least if the graph is planar, then we have this fact, it's due to Castelline. The fact that if, or for gamma embedded in the plane, there exists some operator k. So that's of course really not a precise statement. I mean, but it's an operator that has size the number of vertices, so it's really computable. So such that the determinant this operator is z d gamma x square, actually. It's actually what you get is a skew symmetric matrix, and what you need to take is the Pfaffian. Okay, and so I was very hopeful when I found these tricks that it will extend very nicely to perfect matching. Actually, it doesn't work that well, so I'm just going to state as a proposition. It's the fact, actually, the only covering where it works is the covering with, it's a cyclic cover of odd order, and that's it. So it never works otherwise. But I'm going to state this, so let's say that gamma is a graph that is embedded in the plane. I will write it as C star, so you have 0 in the inner face. Let gamma tilde be the lift of gamma by the map sending z to zd, z to the power d. Then, if d is odd, the dimer partition function for gamma divides this one. And you can check it. There are quite funny examples to try. I mean, you can just try, for example, just take x, y, and then you just, with 0 here, and then you just lift this to x, y, x, y, x, y. Then you just compute the partition function, and you see that if you do this an odd number of times, it works, even doesn't. Of course, so this is not the only, that's just a silly example. Here you take any planar graph, it can be quite a huge graph, and then you lift it in this way, it will work. Okay, but it was a little bit disappointing. The problem is that this matrix, so first, this thing only works for planar graphs, so you need a planar graph covering another planar graph. And then this matrix depends on an orientation, this time an orientation of the edge, and it needs to lift in the right way. So that's not, so it's a little bit more tricky. And this is why I didn't want to talk so much about this. And maybe, so I have 2 more minutes, is that right?
Well, yes.
Thank you.
2 more minutes.
Okay. So I'm just going to give you a very, very small outlook of the kind of things that I'm working on now. And again, this is slightly off topic, but it's really a consequence of this theorem, so I do want to tell you a teeny bit about this. So imagine that you have a graph. Now, I'm not going to write sentences, okay? I'm just going to be. So you have a graph that has what physicists call periodic boundary conditions. Okay? What this means is actually for us, it's embedded in the torus, right? So here you have a torus. And you have your graph that is embedded in the torus. What you can do, because the torus has 0 Euler characteristic, you can cover it by itself. So what you can do here, for example, you take, let's say, n times n copies of your graph. You just connect them this way. And this will still be embedded in the torus, right? So let's call this gamma. Let's call this gamma n. And what people are really interested in this these models is really when you take the limit, n being big, right? So understand the dimer partition function for gamma n for n big. Okay, how does it, how does it grow, etc. And in the case of the torus, it has been done. So that's a result of Kenyon, Sun, and Wilson, maybe 3-4 years ago. What they prove is that if you take, that this thing has the following asymptotic, so it's exponential of something called the free energy of the graph times n square plus small o of 1. And what is interesting, so this is not difficult to prove, so this thing is called the free energy of the model. And it depends on the graph. But what is interesting is that here, sometimes, that is when the model is critical, you have some other terms that appear, and these are called finite size corrections. And what happens is that this is universal. It does not depend on the graph. Okay? And so this is something very interesting. This thing, again, it just computes how the number of perfect matchings explode, when you take this n. But here you really have something that is, and of course it depends on the graph. But then you have something here that is universal. So that's the really amazing fact of this when you understand this asymptotics. So this is not my result. This is something that was done again, so Kenyon and Wilson. But now let's just twist this thing a little bit and let's say, okay, now I'm not going to look at this with periodic boundary conditions, but with periodic anti-periodic boundary conditions, right? We all know that this means it's embedded in the Klein bottle. The Klein bottle, it still has Euler characteristic 0. You still can do this trick. So now I would put the gamma in the other side like this. And you do have the same question that happens. And people didn't study this, and why? Well, why is it not the case? My understanding is that because if you want to understand this thing here, you need to have a tool that allows you to understand how the operator that you're working with will behave with respect to these bigger and bigger coverings. And they had this in the case of the torus, because the torus, the covering is abelian. So then you will have an abelian representation. It will split into just linear ones. And what they just needed was the twisted operator, twisted by one-dimensional representation. This is not rocket science. And they did it just by hand. It's not, they didn't have this, but it's just easy. So, but if you have a cover like this one, that is actually a little bit more complicated. Here it's not abelian in particular. Then, well, it's tricky. You will need to have, your representation will factor into one-dimensional ones, but also two-dimensional ones. So you will actually have to study this operator with twisted by two-dimensional representations. And then you actually, well, so I was able to prove for gamma bipartite graph, I was able to obtain exactly this kind of result for the periodic, anti-periodic boundary conditions. So computation of the free energy, this is not new. I mean, this was known. But then I also obtained finite size corrections that are also universal in this case, but that are different from the torus ones. Okay, thank you very much.